Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host Pedro Abreu, and today Dan joins me to talk with Andrew Marmaduke, a PhD candidate from the University of Iowa who works under Aaron Stump and has been working on Cedille2. In this conversation, we talk about math, foundations, design choices behind Cedille, and what made him change his mind and start working on Cedille2. Before we get into this episode, I'd like to remind you guys that we now have a Discord, and you can find the link to join us on our website, typetheoryforall.com. We also accept donations and contributions of any amount through our Ko-Fi platform. Monthly subscribers have the exclusive perk of watching the recordings live. So go to our website today, typetheoryforall.com, and become a subscriber. With that out of the way, let's get into this episode. Hello, everyone. Welcome back to one more episode of the Type Theory for All podcast. As always, this is your host, Pedro Abreu. And today with me, I have Dan is back to co-host this episode. Welcome to the show, Dan Pluken. Did I get this right this time?
No, not even close, but I'm happy to be here. I'm Dan.
Teach me again, one more time, how to say it.
Pluken. Yeah.
Why do you have a Y over there if you don't say it?
It wasn't my job to add that.
So tell me, man. So you graduated, you finished your PhD.
I passed my dissertation. I mean, my defense, and now I'm, doing the final finishing touches. But so yeah, I'm close to being Dr. Dan the Garbage Man, working on garbage collection.
That is a great title.
I really hate that title. I don't know why I'm giving this fuel to people, but
that's it. It's gonna stuck now. It's gonna get stuck now.
Okay.
So what's ahead?
I'm now a postdoc for the University of Southern Denmark, working with Fabrizio Montesi. Specifically, we're working on choreographic programming, and I'm kind of bringing some of my experience with actors into that domain. I'm really pretty excited about that. We have some projects lined up. If they can get through the damn publication pipeline, we'll see about that. But, yeah.
That's really exciting. Congratulations again.
Well, thanks a lot.
And with us, we also have our guest today, Andrew Marmaduke. How are you, man?
Hey, what's up? I'm just here,
So you're in
my bud.
You're in Iowa City?
Yep. Hey, you remember my name.
So okay, maybe even Dan doesn't know this one, but do you want to know the story? Do you want to tell that story?
Do you want me to tell the story? Okay, I mean, I can if you want.
Go for it.
It's really funny to me, but I don't know if you would enjoy it.
I think it's hilarious. It shows how much of a dick I actually am. People might think that I'm a cool guy, but I'm actually a dick. So.
Well, I mean, you're still a cool guy because we're still friends, clearly, right? So that's not the problem. The problem is that, if anything, you're just an originator of funny stories, right? That's your...
Okay, go for it.
Yeah, so when did Pedro and I first meet? Actually, we were visiting Purdue before either of us had accepted a PhD program. I don't know if you had already accepted Purdue at that point, but I had not. And we met there. First time meeting. Pedro's as energetic as, you imagine him to be, or he has when you talk to him. And so he comes up to me after we've kind of done our visit day, and he's like, "Oh my God, I love you guys. We should be friends. Let's be Facebook friends." He sends me a Facebook friend invite. I'm like, "Yeah, okay, this guy's great. I'll, Facebook friend Pedro. Yeah, I remember you." And then so I decided to go to Iowa because I want to work on Cedille, and you go to Purdue because you want to work with, whatever you want to work with there. And then fast forward a couple of years, we meet either it was the MWLPS first or the Aaron's summer thing first. I forget. One of these things happened. I think we met you came for a summer.
Yeah.
To work with Aaron, and then you just completely had no idea who I was.
I had no idea.
And
completely
I was like,
blank.
We're Facebook. You wanted us to be Facebook friends. And apparently that was that evidence, that paper trail was enough for you to be like, oh, I guess.
No, that's the thing. I opened my Facebook and I'm like, there's no way I'm friends with this guy. I've never seen him in my life. And he's like, no, just search Andrew Marmaduke. And then I do it. And to my surprise, he's there. I'm like, dude, no. He just hacked me or some shit. Right? There's no way.
Yeah, Andrew actually incepted into your mind, and then he planted that Facebook friend. Yeah, so that he could get onto the podcast eventually. That was his whole plan.
Yeah.
This is the only reason that we're friends right now. I'm just kidding.
So you already knew. But no, yeah. So yeah, it's been a joke ever since. I think we actually met on some other thing in between, right? The summer school, and then later I went there. Yeah, you were right. But yeah, I was really surprised that I actually knew you, but because my mind, I had no idea. But that's the thing. That's how much of a dick I am. I can seem a nice person, but I'm just oblivious. Anyways, we're not here to talk about me and my dickhead. We are here to talk about Cedille. So let's zoom back a little bit. For those who doesn't know, Aaron Stump, you still work with Aaron Stump, right? Like he's our advisor.
Yeah.
Formally, he's not there in Iowa anymore. What's the deal?
Yeah. So he's in, I forget which. I think it's I honestly don't remember. I think it's Boston, but for a little bit, like a year, because his wife got like a pretty prestigious postdoc. So, but he's teaching remotely, advising remotely for this year.
So he's coming back to get you graduated.
I mean, he can get me graduated remotely. That's fine. But he
gotcha.
he may or may not be coming back. I don't know. It really just depends, right? I think it's kind of up in the air at the moment.
What are your next plans? When do you plan to graduate?
Yeah, so the current plan is to graduate next semester, maybe summer if things go really.
So you're writing already?
Awry.
Writing your thesis?
Yeah. I'm fleshing out the proofs, writing a thesis right now. That's the plan.
Right,
we'll see.
Okay. Are you teaching again this semester? You were teaching this summer?
I was on an internship this summer. I'm a TA this semester. I taught or was the instructor, sole responsibility instructor for algorithms a while ago, but since then I've just been TA. I
saw somewhere, I think I opened your website sometime because I was trying to find your email, to find your invite, which was really hard. So you don't want to be found apparently, but I found something, and I saw that you have some background in competitive programming.
Yeah, that's many moons ago at this point.
We're getting old, aren't we?
Yeah. Back when I was at the University of Akron, I was a volunteer coach for their competitive programming team, because I was also on the team when I was at University of Akron. I mean, we never like went to Worlds or anything, but we always punched way higher than we had any business doing, right? Because we were competing against the likes of like CMU and Waterloo.
Ooh, that's a big deal.
Basically, first, and CMU would send 5 teams, right? So the first 5 places, another question, never happened.
I actually never asked you this, but what's your story to get into programming languages and type theory? Yeah,
because I started as applied math.
You're a math student?
Yeah, I was applied math, and this is a very corny story, but I'll go ahead and tell you. I discovered a bug in sorry, this story is so long ago that I had to like process it from from the hard disk and like load it up into cache. It's like, what happened again? Oh man, yeah. So there was a bug in my thesis, right? In fact, it was a bug in like the way I did a derivative or something. So I had this like thing where I was doing coarse-grained carbon nanotubes, and I had a bug where my carbon nanotubes could only bend to 90 degrees. They couldn't bend any further than that. It was like a mathematical block. And that was really annoying. So I had like an existential crisis as a young master's student. And I was like, man, how can I never make this mistake again? And then I wandered into a book and happened to pick up Girard's The Blind Spot, which is like more a philosophy book than it is anything else. And if you've ever read Girard's writing, you'll learn very quickly that he's a very opinionated person, and you probably either love or hate him very quickly. but I liked it. So I read The Blind Spot and like learned all about System F and Prolog and all these things. I was like, wow. And then Vygotsky was around at the time, so I started watching him, and he was talking about like the same thing. And so at that point, I was like, man, I really need to shift and stop doing applied mathematics and like differential equations and do logic instead. But what ends up happening is that in the math world, absolutely no one cares about logic in the slightest.
Right, it's true.
Not at
it's
all.
True.
So so I had to do computer science instead.
It went extremely out of fashion to think about foundations after foundations was kind of sad.
yeah, they're like. I mean, maybe it's changing because of Lean, right? Because of MathLib, but back then, no one cared.
But still, Lean is not really great to talk about foundations either, because it threw everything away to do math, right? But still, it brings kind of like the discussion back into the table, which is nice.
Yeah. I mean, I'm a logical pluralist, right? I don't think there's one true logic. So there's room in the world for many, in my opinion, but
there's room in the world for many logics.
Yeah.
Okay. You know, there is this logic that is, what's the name? Paraconsistent logic. That is the weirdest shit I've ever seen in my life, right? Because you don't care. No. It's weird because I don't understand. I have no idea what's going on. But you don't care about consistency, right? In a way.
Not in the same way, yeah. So you allow some contradictions without throwing out the whole kitchen sink, usually is the idea.
Yeah.
But basically, usually what happens is that your negation never behaves like the negation you expect, which is fine because that doesn't happen in intuitionistic logic anyway, right? We don't exclude them.
Right. They don't care about that, yeah.
The negation can be a little funny, that's fine.
Oh, Dan, you have a look in your face that you're completely lost right now. What's in your mind?
No, I'm following along. My advisor's advisor actually, after he became an emeritus, got really into paraconsistent logic, and he started publishing, just releasing drafts of papers in like Microsoft Word with a whole bunch of stuff about paraconsistency. And I didn't understand any of it. I talked to him at one point about it, and he was like, this is a real big issue. And I was like, I'm working on garbage collection. I don't know anything about this.
Oh, that's awesome. Okay, how about we shift gears now and start talking about Cedille2?
Yeah, okay, maybe let's tell the Cedille story, I guess. So what is Cedille in the first place? Cedille is basically this idea of looking at the existing state of proof assistance and the history of impredicativity, in particular, impredicative set, right? Because there's this distinction between impredicative propositions, which are types where you either consider it to be empty or it has a single inhabitant, like their singleton, or impredicative sets where you think of it having like data in there, right? So a natural number is data, it is more than one thing. An impredicative quantification is basically saying I quantify over the set of all things, so that if you define a thing in there, I have actually quantified over that thing already. Like as an analogy, you could think of like a paragraph that has a sentence in it that describes itself, right? For all sentences, this is the third in this paragraph. That's like an impredicative quantification. So Cedille, the idea is like, okay, well, people really don't like impredicative set. There's only one proof assistant right now, Coq, which still has it, and it's basically the prevailing wisdom is please don't use it. In fact, we actually someone in our group submitted a paper where they used impredicative set, and a reviewer just got really mad. It's like,
oh yeah, that was the paper I was in.
Impredicative set, and you didn't mention it. I think they did mention it. I don't know the full details, but they got pretty annoyed about that.
Yeah.
Because Coq, the maintainers of Coq, I guess, don't really test that particular feature flag that much. So instead, Cedille says, you know what, let's just hard commit to impredicative set. Let's go full ham on that against the prevailing wisdom that it's bad. And also, you know what, let's use lambda encodings instead of built-in inductive types. So the big problem with lambda encodings is the prevailing wisdom first is that you couldn't have inductive types. at least in the calculus of construction, this is a proven fact. But it's not clear exactly what you would want to add or how you would add it. That would be better than just stapling on like a natural number type. And the second problem was lambda encodings were so-called inefficient, right? So if you do a basic church encoding, then the predecessor function for the natural numbers takes a linear number of beta steps. Given you have to be really careful when you talk about efficiency when it comes to the lambda calculus, because what model of reduction,
right?
Are you talking about an abstract machine? Are you talking about call by name, call by value? But because you're talking about like a basic natural number to natural number function, it doesn't matter too much, right? As long as we restrict ourselves to nat functions, predecessor is an O of n operation on church encodings, unless you do something really weird with your evaluator of the lambda calculus, right? So there's these two big problems. Well, this big problem of how do you get efficient inductive data, and these other design choices of, well, we're just going to use lambda encodings and we're going to use impredicative quantification to do it. So that's like the motivation. Way back when, 6 years at this point in the past. And so how it was accomplished. And okay, I'm going to give you my perspective on things here because I don't know if Aaron would necessarily agree with this perspective, but hey, I'm here talking, so it's going to be mine. So from my perspective, what Cedille really does to accomplish this is it kind of separates proof from object, and object here is not object in object-oriented programming. Really, I'm just talking about if you have studied first-order logic in any detail, whenever they start talking about quantification, they always introduce, okay, so we have some domain of individuals, and you can quantify over that thing, whatever the individuals are, and then there's so much ink spilt in philosophy over that domain. It's like, does it include fantasy creatures? Does it include Sherlock Holmes? Does it include every possible world? Blah, 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 blah. Right, so there's a lot of ink spilt on what that domain is. But in dependent type theory, that domain implicitly has always been the set of proofs of the type, right? Right, when you do Martin law of type theory and you add dependent types and you do a dependent type over the natural numbers, the only thing that you're talking about is the proofs of those natural numbers. And so in my mind, the real thing that's happening in Cedille, the real interesting idea is that you split it. You say, no, my domain of quantification is not proofs anymore. Right? I still care about proofs. Proofs are still important for deciding that a thing is an inhabitant of a type. But each proof can get projected into this domain of objects. And when I construct a dependent type, I'm quantifying over the set of objects now, not the set of proofs. All right, set, when I say set, these can be theoretically not sets, but for simplicity, we'll call them sets. So for instance, the natural numbers, you may have to do a lot of kind of types stuff to get the natural numbers put together. But when you take its erasure, when you take its projection into the object, it's just a lambda term. That's all it is. And now, so that, because, when you're doing dependent type theory, you have to talk about convertibility between proofs. Now, objects, you're just talking about convertibility between lambda terms. So you can have a bunch of type information disappear. And so that's where these things like erased arrows become important, because they get erased, right? They're only in the proof. They're not in the object. That's where dependent intersections become important, which is really a kind of object refinement. I mean, it's an intersection because you're intersecting the sets of objects, so it's a perfectly good name, but it can be a little confusing because you're not actually producing an intersection in the standard sense that you would say in the literature. But, if you take a dependent intersection of two types, what you're saying is they're different proofs, but they're the same object. That's all you're really saying at the end of the day. And then you have to have some notion of equality, and this is where I think Cedille kind of went a little too crazy, in my opinion. But Cedille 1 says okay, well, if objects are all we care about, then our equality will just be over objects, no type information at all, and then we'll have rewriting and all these things relative to that. So it's a very primitive notion, built-in primitive notion of equality, which gives you the ability to reason equationally, and then those three pieces plus calculus of constructions is enough to derive a lot of crazy stuff. In nested inductive data, index inductive data, inductive data,
So that built-in notion of equality is kind of problematic because it's like too precise that you can only say that this thing is the same as this thing if they beta reduce to the exact same term. Like you can't do like homotopy type theory or something like that. What's your beef with equality and Cedille?
Yeah. So that's you're right on track. In fact, but it's much worse than not being able to do homotopy type theory. Because even if you kind of fix it, homotopy type theory is still out of the question. But your exact insight there of that it's too precise is because it makes function extensionality impossible. In fact, it makes the system anti-function extensionality. Right? You can prove that function extensionality is in fact not a theorem.
So you wouldn't be able to prove that insertion sort is the same as merge sort, for example.
No, it's out of the question. You can't even add function extensionality as an axiom. I mean, you could still you could still theoretically prove it, I guess, right? Because you could add some predicate relation that encodes the idea and then prove it relative to that relation, but you can't prove it relative to the built-in equality. And the way you may.
Well, why not just have that relation then? Maybe this built-in equality is some very precise notion of equality. I guess I don't know.
Are you saying why not replace the built-in equality with that relation, or why not?
No,
just use
I'm saying what's the big deal if you can introduce your own relation that gives you the equality that you want? Why not do that?
Well, now you're getting to in the so-called Cedoid hell space of things.
Oh, okay.
That's a technical term, Cedoid hell. So, the problem is that the built-in equality kind of is like viral, right? And this isn't just because we had a pandemic a couple of years ago that I'm going to start introducing virality analogies. But equality is viral because you want the substitution property, right? If P of A holds, A is equal to B, then P of B better hold. So that means that equality effectively is touching everything, right? It has an impact everywhere because you have to have this kind of substitution property. Or at least you really want it, obviously, or else it's really not an equality, right? It'd be a very impoverished thing if you didn't have this ability. And when you postulate your own relation, now you have to prove that all of these predicates respect the relation in order to get the substitution property, right? So you kind of, everywhere you're proving that predicates are respecting the relation instead of just having it for free.
That makes a lot of sense to me. So let's summarize this to make sure that everybody's on track, all the listeners are on track. So you've got this proof assistant Cedille that has been built. I'm not a type theorist. I'm going to misuse so much terminology here.
Yeah, no, it's fine. I don't care.
The direction that you were going, there were three things that you mentioned. You were talking about going all in on impredicativity. Then you were talking about going all in on lambda encodings in order to get rid of these additional inductive data types, which I think were like a hairy thing to deal with. And the last thing is this hairy notion of equality. I'm starting to confuse what Cedille did compared to everything else versus what you're trying to do with Cedille2. Because you're probably still buying in on the lambda encodings and stuff with Cedille2, right?
Yeah. So, sorry, I haven't even really talked about Cedille2 at this point. It's really just only been the Cedille1, I guess we'll call it.
Well, let's make sure that we're all on the same page, because Pedro's been making the exact same face this entire this entire point when we were talking about Cedille. I was wondering if he wanted to stay on that.
I'm very happy to do a wrap up. Like let's make sure that we got everything here that we're talking about Cedille. So what are the things here that makes Cedille? We have this dependent intersection, right?
Yep.
And dependent intersection is talking. How did you describe it again? You have two objects that they are the same, but their implementation are different, or their proofs are different. Is something along those lines?
Yeah. So here's maybe another way of thinking about it. So in Cedille, every term has an erasure, which just takes the term and constructs an untyped lambda calculus term. Dependent intersection, really, at the end of the day, is a dependent pair, except the erasures of the first and second component have to be equal.
Right. And then you must have this notion of equality in order for you to talk about about what it means to have this independent intersection to begin with. And the equality in this case is a very syntactic equality. What exactly this equality looks like?
I mean, yeah, it's literally just you give it two terms, and that's it. And it just says, okay, are their erasures the same? And it's a propositional equality, of course, right? So you still have rewriting. You can still prove propositional equality, just like you would in any equality you see in any other proof assistant. The only major difference is that it's untyped, right? It's over the erasures only.
Mm-hmm. Mm-hmm. Well, I mean, so I'm trying to make sure that I get right the notion of equality here, because equality is super hard, and there are a few different ways to define equality. For example, there's Leibniz equality, right? There are some different notions. So, and since it's been a while, I hacked around with Cedille. I used to do some work there as well. But it's a very syntactic, right? Like, just look at the lambda terms and they have to like really match, something along those lines, right?
Yeah, I mean, yeah, it's honestly important to kind of fully understand this point, because when we do get to Cedille2, the equality is the very thing that changes.
Right. Oh, okay. Yeah. Nice.
Yeah, so if you want to prove, here's some kind of funny consequences of Cedille's equality. Suppose you encode list and natural number. You can do this in a way so where nil, the nil constructor for list, and zero, the zero constructor for nat, have the same erasure. Which means you can prove internally that nil is equal to 0.
Right, yeah.
Right?
So,
and now, whenever you have these predicates, right, you can have a predicate over lists, but because equality doesn't care about types at all, right, theoretically, 0 holds in that predicate too. Right, so
does this lead to inconsistency?
No, actually, no. Surprisingly, not. It leads to
so it's just
non-termination.
a weird consistent system where lists are the same as numbers.
No, not this. Just 0 and nil, right? Because cons is different from successor.
Well, it kind of reminds me of set theory, right? Where you have the exact same encoding problem. This set is represented the exact same way.
Yeah,
that's interesting.
Yep.
It's not a problem. I see it more as a feature, right? Because you can write the same program for lists or parts of lists and parts of natural numbers, right? Like the same program that holds for nil will automatically, for free, also holds for 0, right? Things like that.
Yeah, this is a great point of contention. Is it a feature or is it a bug? Cedille would obviously say it's a feature, and we still want something like that in Cedille2. Right, so this gets to a certain point about inductive data types, right? Because some people would say inductive data types really aren't that complicated. Just staple the darn thing on. It's not that bad. Every proof of system does it. And I have a lot of sympathy from that perspective. But there's like more to not building in inductive data types than just not having to implement them in your core checker. And one aspect of that is you get to explore different kinds of inductive data types, right? You get to explore different ways of putting them together. So
just one addendum before you continue. People who say that it's trivial to put that inductive data types inside your languages because never implemented them and doesn't know how hairy the meta theory actually gets, especially when you're talking about elimination, like pattern matching and things like that. It's tricky. It is tricky. There's a lot of ongoing research on that field, especially because you have no idea how equality actually behaves, right? Things like that. Yeah. But anyways, go on, please.
Yeah. Well, I mean, so even if we give them the idea that it is not that tricky, or at least not as tricky as impredicativity, you get to experiment. And so one experiment we discovered with this kind of encoding bug, or as we like to think of it as a feature, is that you can set up your inductive data types to where they interact and build up very nicely, right? So you can do this kind of data types a la carte stuff, where you say, okay, I'm just going to have a label for the zero constructor and a label for the cons constructor, and I will piece them together using a dependent intersection, actually, right? And then I could add another constructor later on, and I'll have a cast from the first one to the next one. So like the prototypical example I like to use is you can build up the natural numbers with zero and successor, then you can add a predecessor constructor, and then you can cast from the nat to the int, because they share the same shape, if you want to call it that, of constructors, right? because they are encoded in such a precise way that the objects end up being exactly the same. And maybe you don't like this, maybe you really don't like the encoding problem, but at the very least, this demonstrates to other systems, hey, you could have this as your inductive data types, and you just, you could staple on an inductive data types that have these principles, because we know that you can model it in Cedille.
Right. One thing that I was gonna say is that I thought it was funny that you compare this work with data types a la carte, because in a sense what you're doing is like there is something more principled, more fundamental that data types a la carte itself also breathes from, right? And that's where you guys are going for doing the Cedille things, which are the lambda encodings itself, right? So for those who are not familiar with data types a la carte, it's really going back to the thing of breaking down your data types back to this notion of some more fundamental encoding, right? And there we have the cat. And
she got really mad at you. Whatever you said, I don't know, man. Walk it back.
Doesn't like some encodings over there, lambda encodings and things like that. So my point being is that the sort of things that is being implemented in Cedille is exactly this notion of going back to this more principled fundamental notion of lambda encoding, that you don't even need to have the data types in your language to begin with, right? And then from there are some interesting properties that you'll be able to derive from, especially you're talking in particular about casting, right?
Yeah.
Mm-hmm.
I mean, this is kind of the tagline of Cedille,
okay.
Which is, Cedille is all about finding as many complicated ways to type the identity function as possible.
That's a good way to put it. I like that. So then, did he answer your question? Are we being able to follow things? I'm using you to give us a track if things are getting too abstract here.
Yeah, I'm definitely the lowest common denominator on this case. But so I've lost track of the thread of where we were going. So far we've been talking mostly about Cedille, and then we were talking a little bit about Cedille2 in terms of this new notion of equality. Is that right?
No, I mean, we really haven't talked about Cedille2 at all. This is all Cedille.
All right. So what made you to be like, fuck Cedille, let's go Cedille2?
Yeah, well, I mean, I really like Cedille, but I do think that the equality that was picked was a mistake. So the idea was, can we change the equality, in particular, so that we can get strong normalization back, right? Because one of the biggest issues with Cedille is that you lose strong normalization. You lose normalization, period, right? So you can have non-terminating terms. Always in a inconsistent context. Right, so that's why it doesn't mess with consistency. You have to have false in your context in order to get this non-termination. But funnily enough, sorry, I have to talk about this little side note. Exact same problem happens in lean. so maybe it's really not that big of a deal, but here we are.
So wait, what's the problem exactly again?
So if you're in lean, because they have this proof irrelevant equality type, and this may be lean 3. I don't actually know. Because there are so many leans, I don't know if this happens in lean 4. I believe it still does because they have casts in lean 4.
Mm-hmm, right.
But because they have this kind of proof irrelevant equality eliminator where you actually don't talk about the input equality, there's this paper by Cockwind and someone else, maybe Abel. Sorry, I forgot your name. That showed
Andrew Isabel, probably.
Yeah, that showed that you can derive non-terminating terms if you have false, or if you have some false equivalent proposition hypothesized. But lean is consistent. It has a pretty, in my opinion, straight edge model in set theory. There's no problems there. Seems consistent to me. But also, lean, when people were lean, no one cares, right? Yeah. And it was a very similar experience in Cedille. We're non-terminating, never mattered in our experience. But all that being said, it still is an interesting question of is the non-termination Cedille really necessary to kind of accomplish the goals it does accomplish? And so the way that I went about fixing this, to spoil the question, is I don't think it is necessary at all. The way I went about fixing this is to say, okay, remove the equality as it is, just get it out of there, and let's just plop in Martin-Löw's standard identity type and see how far we can get. Right? Where does the initial construction that we've always been doing, where does that fall apart? And it turns out it falls apart basically at 3 spots. The first is the indices. They have to be erased. Fine. Okay, we'll modify the Martin-Löw identity type so that the indices are erased. No big deal.
What indices?
For the identity type, it has a type parameter and then 2 indices, the left hand side and the right hand side of the equation.
Mm-hmm.
Right, so that when you're specifying the identity type, those inputs have to be an erased arrow, right? They can't be used relevantly in the term. Right, so they're not going to show up in erasure.
Mm-hmm.
So you have to erase indices. You also have to erase the input to REFL. And this is like there's a very interesting consequence of this happening, or like making this decision, right? Because if you think about homotopy type theory for a second, what is it, or at least this is my perspective of what it's saying. You have a REFL constructor and it takes an input. Well, if you kind of squint, that's a function space, right? REFL is a function that takes an input. So you have a function space worth of room to do stuff. That's why you can't just say REFL is a constant. And also why you can fit in a lot of information in there, i.e. homotopy type theory, because you have enough wiggle room to do a lot of stuff. But if you make the argument erased, then when you erase it, REFL can only be a constant, right? There's no room for it to be anything else.
Everything out, yep.
Right? So what happens?
What's that argument? Sorry, what's the argument of REFL?
So if REFL is typed at A equals A, right? So the argument will be A. It basically proves it proves a trivial equality given a particular input.
Mm-hmm. Okay. But then what is it a proof of? Oh, it's a proof of any A equals A.
Yeah, so for any one particular guy, you can prove that you have reflexivity for that guy.
And turns out that's pretty much all you need for equality. When you use equality in Cog, for example, that's what you're doing.
Yeah, that's
which is very surprising.
Yeah.
But so this is what we call propositional equality. But it doesn't have it has indices you were talking? This in this case it doesn't, right? This data type, there are no indices, because that would be heterogeneous equality, which is not what we were talking about, right?
No. So if you like write down the identity type in Coq, what do? You say, okay, I have a parameter A, which is a type,
right?
And then I take there are a lot of ways of doing this, but the typical way is you say I have another parameter, the left hand side, which is of type A, and then I have one index, right, eta star, and that index is the right hand side, and then my constructor REFL is give me an A, and then it's it A. Or in Coq you have to write the parameters too, I think. So
right. So you have the parameter A, but then the index is something of this A, right? Like it's an element of this A.
Yeah, and it's equivalent to make both left hand side and right hand side also, but make them both indices. That's the same as making just the right hand side an index.
Okay, I can go with that. So what's the problem with that?
Yeah, so if you don't make these things indices, then when you do like induction, right? Because we've added the Martin-Löw identity type, so we have the J rule, we have induction. What happens is that the indices show up in the erased term, and that means that the objects don't match. And so that, because we're doing Cedille, we want the objects to match. We're doing very precise encoding. So you just erase them. And it's also kind of like the least, in my opinion, problematic thing, because when we're compiling functional programs, we're already erasing indices anyway. Right? When you compile the vector type, you just erase the natural number that's encoding its length, right? It's a known fact that you can erase that thing and it's not going to cause any problems.
Let me back us up for a second. What does equality have to do with non-termination?
Yeah, so unfortunately this is a bit technical, but what ends up happening is let me try to first explain it via analogy. If you have an equality, if you posit an equality that is just bogus, like true equals false, and then you use it, you're using it clearly in a context that is inconsistent because you've posited a bogus equality. But if you use it in a way to where that equality term gets erased or is irrelevant somehow, then its lack of evidence will not block certain reductions that it would have blocked otherwise, right? It acts almost like a gatekeeper of saying, okay, well, I can turn this type into that type, and you can do this application and that application, but only if you tell me that this equality actually holds, right? So it's like this little gatekeeper. But if it disappears, then all of a sudden you just boop, you have the term, and you can like build delta pretty trivially, and from delta build omega like almost immediately.
Okay, wow. Yeah, now I get it.
Yeah, so I mean, reading this Cochrane paper, maybe I should actually look for that, but I'll have Pedro put it.
Yeah.
I can give Pedro work.
Yeah.
I'll find it for you, and you can put it in the after meeting notes so people can look at it. But yeah, it's like it's just like little technical construction that says that if you get to ignore equality proofs, then you get to build delta, and you're off to the resources after that.
I think there is one more thing that is in my mind right now that we didn't talk about that I think should be mentioned for Cedille, which is that of extrinsic. What's the name? Extrinsic typing.
Oh, this Curry style versus church style, or
right.
Extrinsic versus intrinsic.
Is that right? Like that makes a lot of difference when we're talking about intersection types and all this notion of equality, because that only makes sense in the notion of extrinsic typing, right?
Yeah. So here's the thing. I don't think that's even true, right? I think that was kind of a red herring, in my opinion.
Huh. Okay.
Because Cedille2 is very church style.
Give a brief overview what that means.
Yeah. Okay. So let's do intrinsic, extrinsic, because I personally don't like using people's names to name important stuff.
There are too many. There are already a lot of things that use church or Curry name. Like, why one more, right? Come on.
Yeah. So the extrinsic style is the idea that you just have a programming language, in this case the lambda calculus, and types are added as annotations, but they're not really part of the language. They're just annotations. Maybe when you're writing the language down, you'll write the annotations just so you have decidable type inference or whatever. But at the end of the day, the language is the thing underneath. It's the erasure. It's the untyped lambda calculus. Right, so you can see now why Cedille is like kind of following this philosophy, obviously, because that's, under the hood, that's kind of the idea, is that, the objects are really the untyped lambda calculus, and it's not the proofs. On the other side of the spectrum is intrinsic, which says, no, the types are integral. They are what makes the term meaningful in a certain sense, right? If you don't have the types, you don't understand what that term really means. And this is more a proof theory perspective, right? So if you want to say that you have a proof of a thing, you have to have all the type information, all the indice information, all this extra information, so that you can always reconstruct the type from the proof, right? This is an important philosophical point of what is a proof, and most people would seem to agree that you don't have a proof if the proof doesn't, have enough information to encode that it is a proof of a given type. Right, so you have to have all that information in there. Is that enough, or should I give you a little bit more to understand?
That's with Dan.
It made sense to me.
Yeah. Okay.
Right. Okay. So the reason why I think this is just a bit of a red herring in Cedille is because you can do all the intrinsic stuff. You can still do all of that. The only extra thing you add is that there's a projection to a new space of objects. And convertibility of your proofs is relative to objects, but that doesn't mean you lose the proof. You still have the proof. You're just saying that, oh, my proofs have this extra structure where they can become objects if needed. And you're also saying that my quantification domain is over objects, not proofs, because I don't particularly care about quantifying over proofs. They're just, that part's not super interesting to me. Which is why it's like now it becomes the dependent intersection, which was like this very interesting kind of crazy extrinsically viewed object. It's really just a dependent pair, right? At the end of the day, it just becomes a very standard dependent pair with this extra side condition that the objects are the same. Very not crazy at all.
But that's the thing. You can only do this side condition if you're not tied for the notion that in order for you to even have the term, you need the types, right? So you can only do this comparison if you ignore the types in this case, right?
No, you could do the exact same thing in any church system.
Yeah? Okay.
Right? You just say that they're convertible. That doesn't mean you might not be able to inhabit it with anything interesting, right? It might be like a very boring type, but you can absolutely state it.
Do you need extra steps to do that in a church system, though?
No. Well, I mean,
no?
Okay. If you're taking the way that I've constructed Cedille2, absolutely not. No, it's like
okay, go on. Mm-hmm. So Cedille2 is still extrinsic.
Cedille2 is intrinsic.
Oh yeah.
Yeah.
Okay.
In my opinion, I mean, there is this kind of like extra step that you include erasure, and convertibility is relative to erasure. But in my opinion, it's an intrinsic theory.
Okay. Now let's then talk about the differences.
Yeah. So the main difference is equality, right? Equality gets removed from Cedille 1, and we add on Martin law of equality, or we try to start with Martin law of equality for Cedille 2. And as we discussed, okay, well that doesn't quite work. We have to make the indices erased.
Okay.
And we also have to make the input to reflexivity erased.
So is Martin-Löf equality the same thing as propositional equality?
It is the thing that when you postulate it in Coq, it's the very type
right.
you're thinking of, yeah.
EQ and with Raffle and...
Yeah.
Okay, right. So when you're talking about like Martin-Löf things, you usually say that the word identity. So that's identity, I can have the same idea as identity and EQ being kind of like, we're talking about the same thing.
Yeah.
Okay.
Yeah.
Cool.
Yeah, so it's Martin-Löf's identity type.
Mm-hmm.
Yeah, so I guess, where was I? I was talking about like this interesting thing about reflexivity, where you make the argument erased, and what happens there, the reflexivity has to be a constant, which means uniqueness of identity proofs is internally provable. Which is like this big, this is like the homotopy type theory's bread and butter, is that in Martin-Löf type theory, you don't have uniqueness of identity proofs for free, or you can't prove it internally, so you get to take this other road. So in Cedille, it's like it ends up being integral, right? At the end of the day, uniqueness of identity proofs is kind of integral to Cedille and what it does and what it accomplishes. Maybe you could do some kind of homotopy type theory stuff using the same ideas, but it's definitely not happening in the system as it's currently stated.
So a quick reminder, like what is the impact of having uniqueness of identity proofs in Cedille 2? Yeah,
so it means that whenever you have two proofs of identity at the same type, they are necessarily equal themselves.
Mm-hmm. But what does that imply? What's the greater implication of that? Or it's just like a meta-theoretical implication?
I mean, so the downside of things is you can't have univalence. On the upside of things, pattern matching becomes easier. Though I think the AGDA people have done like a good job of making pattern matching still work in cubicle. On an upside, one upside, which happens in Cedille, is because you have UI. I'm going to call it UIP, uniqueness of identity proofs. Construction of inductive types becomes pretty straightforward because you're just constructing the set. You're not constructing this giant hierarchy of stuff.
Oh, you're referring to universes there?
No, right? When you construct a inductive type in homotopy type theory, the type's not really a set. It's really like an infinity groupoid, right? You have you have to somehow capture all these coherence conditions in your...
Oh, yeah. Right.
Which there is a paper that does do this, also using impredicativity. But yeah, I didn't read the paper in detail, so I don't know how they end up dealing with coherence conditions. They probably just add a quotient type. That's my guess.
But so does this save us from that setoid hell issue that we had at the start? Or how does this relate to that? This new equality?
Well, because this equality is built in, and you have the substitution property, right? So you still have PA, A equal B, PB. You're not going to be dealing with setoid hell relative to that. Also, because the equality is typed, and so it's not as precise, function extensionality, I believe, this is an open question, but I believe, is something you could postulate and use, right? So you're no longer in this situation where the system says function extensionality is not a theorem.
You no longer have the nat equals or 0 equals empty list, right?
You actually can, but you have to go through an intermediate type, right? You have to say, okay, nat and list, they have to cast to some shared type so I can express the equality at that type.
Okay.
It seems to me that the reason for this is because we're back in intrinsic style, right?
Yeah, for sure. Right, Cedille's equality, I mean, even Cedille's original equality, right, could have been expressed intrinsically, right? You could have just said
it could.
a top type or something.
But I feel like originally that's kind of a selling point, right? Because then you get all these casts for free exactly because they're underlying the same term, right?
Yeah, that's 100%. That was the philosophy behind it, and arguably this like guiding principle is why Cedille exists at all. So we shouldn't be too harsh on the extrinsic view of things.
I think it's almost unfair to call Cedille2 then.
Well, I mean, so it's this is a fair point. What makes Cedille2 a Cedille? If you want to argue that. And
right.
there's this critical property that needs to be proven, in my opinion, for it to be a true Cedille, which is that when you have convertibility, you say A is convertible to B. If in order for it to be a real Cedille, that has to be equivalent to saying that the erasure of B equivalent to the erasure of A equivalent to erasure of B. You have to be able to take the erasure first, and that give you the same answer as you taking the erasure last. Mm-hmm. Right, because that is the core of what's happening in Cedille, really, at the end of the day. Is that object equality is enough. It's knuff.
One thing that I'm not sure if it was clear. We were talking. There were some points that there was some time ago that Dan raised the issue of soundness. So. Just to be sure, so Cedille, is it sound or not?
What do you mean by? Do you mean consistent, or what do you mean by sound? Sound relative
consistent,
to what?
Yes,
model?
right. Mm-hmm. Consistent.
Yeah, so Cedille is consistent. It has a realizability model.
There you
go. Which is pretty similar to what Girard would do with system F omega.
Right, and could you derive that for Cedille2 as well?
Well, Cedille2 ends up being a subsystem of Cedille.
Oh yeah.
Funnily enough, so you can just model in Cedille. And boom, you have consistency.
Interesting. Cool.
Or maybe subsystem is not exactly the right word, but you can easily model it in Cedille.
Okay, so the big question is, where is it at in implementation-wise?
Implementation-wise, I mean, nowhere, right?
No?
Right now, I'm trying to, I have drafts of pretty much all of the important proofs, and so it's a matter of like getting those proofs in detail, getting it so a committee agrees that those proofs are correct, and graduating, basically. Right, that's where we're currently at.
Screw implementation. Who needs implementation? We don't need to use these things. Whatever.
Yeah, there's a current goalpost, and we have to reach that goalpost first.
That's good. Yeah. Right.
But I've been trying to like explain Cedille2 in a way to where like if you listen, and if you understand, you'd be like, oh yeah, that's definitely strongly normalizing or whatever. Right, that's why I try to express it like Cedille2 is just an intrinsic type system. Dependent intersections are not scary. They're just dependent pairs with this extra side condition. These kinds of
honestly
familiar explanations.
Dependent pairs are scary enough. if you start actually looking at them, like when you look at from far away, you're like, okay, those are those cute things that are dual to for all quantifiers and all of that, right? Like it's fine. But once you sit down and try to understand what's actually going on, and you're trying to prove things and use those things, they're hard. It's not. I don't think it's trivial at all.
Yeah. Yeah. Well, okay. So here's the. There are some skeletons, right, that we haven't mentioned yet. And by skeletons, I mean actual scary constructs. So the actual scary construct, which is also the reason for non-termination in Cedille, is the phi, the casting rule. Right, and so the casting rule in Cedille says if you have an equality from A to B and you have an A, then you can replace its erasure with the erasure of B.
Which is basically J, but for extrinsic things, right?
It's inspired by New Perl's like direct computation rules.
Oh, interesting. Okay.
That's kind of where it was stolen from in a way, and it's all great artists steal. So.
Yeah, of course. Nothing is created, nothing is lost in science. Everything is stolen.
Of course, yes. So, but this principle is like actually pretty integral, pretty important, and so you have to like make it work in Cedille2 without. The whole goal is to not have it break the system and cause non-termination. So how do you do that? My current answer to this question is you think about it like you're caching the input. So imagine you have a function from A to A intersect B that behaves extensionally like the identity. So for every A, the first projection, so f of A, taking the first projection of that, is equal to A. So it behaves extensionally like the identity. Well, if you have that guy, and you kind of like crack it open and look at how it would be implemented on the inside, the idea is that you cache the input. So you take A, you cache it in some structure, and then you take whatever the actual output is, B, right? So that's the actual thing you computed. And then you take the proof that it behaves like the identity, that B would be extensionally equal to the input A. So it's sorry to say, like, it's hard for me to break this down anymore because this is like the real meat, the real technical difficulty that's going on. But I can try to give it an analogy if you would like, because I saw Pedro's eyes glossing over there. So I know that it's not going too well.
Yeah, sometimes I have a hard time following what people are describing math in my head. It's hard for me.
So think of it this way. Think of it as an analogy. You have some type, and really what you would like to say is that type is a canonical element of a quotient. Right? So you have a fraction, you have 1/2, and really what you would like to say is that's just a quotient. I don't need to do anything. I can just treat it like a rational number already. I don't need to do any canonicalizing. In Coq or something, you would have to run it through the canonizer regardless, right? Because there's no other way to kind of get it to the right type. You have to run it through the canonizer, and that could be an expensive operation. It could be linear in the size of the data. Right, so that's not good. We don't want that. We want to just push it into the type. So the idea in Cedille is you say, okay, I will run the canonizer and also cache the A. So I'll do both of those things. And then I'll also keep over here as a third component a proof that A really was canonical all along.
Okay.
So what happens is now if you're in so-called proof mode, if you're in the proof fragment of what's going on, I'll do reductions in the canonizer. Because that's the proof, right? That's the evidence that I'm moving towards the quotient, moving towards rationals. But if at any point you move to the object land, then the erasure just takes the cached A. Because you know that the object of A and the object of B will be the same thing, so the cached A is enough. Right, so that's how you can like short circuit, in some sense, the computational operation to turn the order, however expensive the canonizer is, and to just taking the A and working with it. Right, so it's kind of weird in a sense because you're like moving compiler optimization stuff into the type system. Like not all of it, obviously, but like some important stuff into the type system in order to not just get efficiency, but also to get, this tagline of how many complicated ways can we type the identity function. And the phi rule is all about that. That's where you get the complicated ways. So I would be remiss if I didn't say this. There's one more complicated side condition to this thing, which is that the free variables of the canonized thing and the proof thing, the free variables used in both of those proofs have to be a subset of the free variables of the thing you cached. Right? And this gets back to that inconsistent context stuff. Right? Basically, it's what it's trying to say, if you think about it almost like a Kripke frame, or just like, a graph of context is also fine. What it's trying to say is that, like, you can't be using more hypotheses, like a more or stronger hypothesis set than what you cached the input as. Because if you are, then those hypotheses could be erased. They can be thrown away. And that's no good, right? We don't want that happening.
So is this all stuff that like a Cedille2 user would have to deal with, or is it handled internally?
So the Cedille2 user, the only thing they would have to do for phi is provide the cached element. It's like writing a pair of three things: the cached element, the canonized function, and the quality proof. The free variable stuff is easily automatically checked.
One thing I'd like to move this conversation to at some point, I don't know if we're still going to discuss this, but is like from a end user perspective, summarizing like the difference between Cedille and Cedille2, and also how Cedille2, when it exists, compares to these existing other proof assistants from like a user perspective. Because I think like we've been very in the weeds so far, and I'd like to kind of come up for air for a second. But if we're still discussing this, we can move that a little bit later.
No, I'm perfectly fine moving on to more speculative stuff. It's certainly more fun, even for me.
Yeah. So going from Cedille to Cedille2, if I understood correctly, from a user perspective, you've got this brand new notion of equality that's, more closer to the type of thing that we want to be working with. For example, you can more easily prove extensional equality of functions. And then there are also some like discussion of efficiency, which I guess would mean that proof checking is faster. Like if you actually run the thing, it will take up less cycles. Is that a good summary of the end user perspective on this stuff?
Yeah, so it could be, right? This is the you get to choose, right? So you could either the proof, so the implementation, sorry, not the user. The implementation gets to choose, right? Because you could be in a situation where there are some meta variables, some unification variables in a proof that you don't want to erase, because if you had done some conversion or some, when you get into an advanced implementation, conversion checking becomes unification, right? I don't know if maybe you guys are not aware of this, but conversion checking becomes unification in any serious implementation. So when you're doing unification, you may want to actually dive into the left-hand side and the right-hand side of a dependent intersection. Because to strictly check conversion, you only have to do the left-hand side. You can completely ignore the right-hand side, but diving into the right-hand side may solve a unification variable for you, right? So you have this interesting choice where you could be faster, or you could look for unification solutions. And at this point in time, I have absolutely no idea how to implement that in the best possible way for an end user, to be honest. But it is nice to mention that you could skip an entire like sets of terms, and it's also important because in Cedille, when you build up these encodings, you're like stacking intersections, so it would be quite a bit more expensive to check those things if you weren't able to ignore the refinements.
Mm-hmm. Do you guys know like how big? So this impacts basically the speed of proof checking ultimately at the end of the day, right?
Yeah.
What? So is that a big thing? Is that a big issue in the proof assistant community?
Absolutely.
Speed of proofs?
Yeah.
Yeah.
Yeah, so Andres Kovacs probably has done the most work in this space of like how can you get an efficient, in the sense of proof checking, dependent type theory implementation with kind of like a modest amount of effort, right? So if you're like a one person developer team. And it basically boils down to normalization by evaluation at the end of the day. There's just saying that, there's like a giant branching structure of choices. But, for the purposes of this discussion, it boils down to normalization by evaluation. That's like the way you want to go.
And so will Cedille2 be faster than the competition? Is this at the end of the day what we're trying to get towards? At least Cedille2 can potentially be faster than Cedille1.
Yeah, well, unfortunately, being faster than Cedille1 is a trivial thing to accomplish, right? If you just follow Andreas Kovacs's plan of action, you'll be really fast in comparison to Cedille1.
Who's this Andreas Kovacs? I don't know him. What does he work with?
He's just like a PL person. I don't know if he has like one particular like specialty, but I can. Okay, more work for Pedro. We'll. Are you familiar with small TT? Actually, maybe this is a better keyword.
Right. Yes.
So Andreas Kovacs is responsible for small TT.
Okay. Good. Gotcha.
Yeah. But to your point, it certainly would be an important avenue to explore. Is can Cedille2 be faster? But the problem is that the existing systems tend to have like these advanced abstract machines. Like Coq has VM compute. And it's not entirely clear to me that you will get many wins over that. I don't know. It's very hard to say at this point.
Mm-hmm. So yeah, I mean, like, what's the future of what's Cedille3? Where are we going with this stuff?
Yeah, I don't know. I have no idea. I have a lot. So it's what's more interesting to me after Cedille2 is like, if Cedille2 hopefully becomes finished and I graduate, that'd be nice. So if that happens, it's more interesting to me what kind of constructions are possible in Cedille2, right? Because that was basically my line of work through my entire history as a PhD student is what kind of things can you build in Cedille? And I still have like a lot of them. Basically, I got to the point where I was like hitting the limits of the implementation system. So I was like, man, I have to implement my own thing because this is really getting annoying. And then that led to like, oh, I actually don't need that. Oh, I actually don't need that. And this can change. And then Cedille came about, and here we are. Yeah, so there's probably not going to be a Cedille3 for the foreseeable future. Sorry, it's the short answer to this question.
Uh-huh. But so there are things that are we trying to get Cedille up to the expressive potential of what Coq and Lean and so on are able to do, or are they disjoint? What is it? What's the Venn diagram?
What do you mean by
overlapping?
By expression?
You were talking about expressivity, like what can I express in Cedille, and then you were running into challenges. It seems like part of what you were trying to do was to make it more expressive. No?
Yeah. Okay. So there are two kinds of expression here. There's like, does the system get in my way of just writing code? That kind of like expression. In which case, Cedille1, you will run into those issues pretty significantly if you're trying to do advanced stuff. But you probably will also run into those issues in any proof of system except Agda. Right? Try to, go write a mutual inductive data type in Lean and tell me how inducting over that goes for you. It's not going to go well. It's going to go pretty horribly. But if you do it in Agda, it's going to be a dream, right? It's going to be really nice. So there's that kind of expression. But then there's like the kind of things I can construct. So in Lean, go try to make an inductive data type. You can't. It's not possible. But in Agda, you can, right? So Cedille is nice. Even Cedille1 is nice in the sense that like it seems to be able to construct just about anything Agda can, right? That's, there's still things to check, but it seems very expressive in the sense of like what theoretical fancy type things can you build if you're willing to put in the effort.
This is an interesting question because I remember I've also done some work on trying to push the boundaries of Cedille and Coq and see what can you really express on those things. And I came to the conclusion that there it comes a point where you really want to have induction recursion, for example, right? Yeah. So my question would be, would that be a possibility in Cedille2, for example? How hard would that be? This is an open
question and is, in fact, the very next question I was going to tackle before I got annoyed with the system and started implementing Cedille2. So if you build inductive, so we have two things already. We have inductive data in Cedille1.
Let's make a
And
pause and explain what are those things. Inductive recursion.
Yeah, so first let's start with what's mutual inductive data. So this is the idea, like you have even and odd, and some of odd's constructors can refer to even, and some of even's constructors can refer to odd, right? So they're kind of mutually defined. Inductive data is an extension of mutual inductive data, where the types become ordered, and the second type can use the first type as an index. So what's an example of that? A list set, right? So you can think of a list and a predicate saying that all of the list's components are unique, right? So the first, the list has a parameter A, whatever, it has nil and cons, but then the second type, which you are mutually defining, takes list as an index and says, okay, well, the nil case is fine, right? That's unique. And if you were to do a cons, then that has to be unique to all the other elements, right? You have to have a proof that it doesn't equal any of the other elements, right? So that is a simple example of an inductive type.
So inductive isn't necessarily mutually recursive, mutually inductive.
No, it is. It must be, yeah.
Because it seems to me that the list doesn't necessarily mention the predicate, does it?
No, it does, right? Because when you do a cons, you basically say that the element of the con satisfies the predicate, so that you know that it's unique.
Okay. Gotcha.
Yeah.
And now mutually recursive. Inductive recursion.
Yeah, so inductive recursion is like inductive, except the predicate can be defined via recursion.
Yeah.
Right, that's different. That's the main
kind of like
instead of via induction, you define it via
right.
recursion. Yeah, so in Cedille, this is like an interesting point, because in order to do the recursive part, you need large eliminations. What is a large elimination? It's the idea that you can compute a type from a value. So you could you could compute some type via recursion of natural numbers. But that's like very difficult to add to Cedille because you don't have built-in inductive data, right? You can't just like staple on the large elimination rule. How do you get it? It's like very unclear. It was very unclear for a while. And if you look back at the history of Cedille, a lot of the early systems they did just kind of add in a large elimination facility because it seemed impossible at the time, at least. But we now know that you can at least simulate large eliminations. And by simulate, we mean you don't get definitional equality of your function. So you can define some function via recursion, but it doesn't definitionally beta reduce. Instead, it casts. Right, so you could write a function, say, by pattern matching over natural numbers, where 0 goes to true and anything else goes to false. Right, you typically use this to prove that 0 is not equal to 1, or something of the like. In Coq or whatever, you just like apply the function on the left and the right via congruence or whatever, and it will automatically reduce to true and false, and you're good to go, because true is not equal to false. But in Cedille, you apply the function, then you have to use a cast rule to actually like force the computation to move forward. Right, so you have to do extra work, but you can still get the same effect. This is why we call it simulated large eliminations instead of true large eliminations. Yeah, so the greater point is, how do you get inductive recursive types? Well, inductive types in Cedille are just, they're actually not that complicated at all. You just use the same construction but make it mutually recursive, which is kind of easy to do with impredicative quantification. But the simulated large elimination, how you define that is actually just an inductive type too. So if simulated large eliminations are just an inductive type, if you have inductive types and simulated large eliminations are inductive types, then if you plug in the inductively defined simulated large elimination to the predicate, you have a simulated inductive recursive type. I'll just end with the punchline, right? We don't have to kind of belabor this point. But I'm pretty confident that you can do inductive recursive types, simulated inductive recursive types in Cedille. That's just the punchline.
So yeah, one thing that I was thinking of here is that I can see why, for example, Coq doesn't have inductive recursion data types, because yeah, reasoning about that sort of stuff would get hairy very quick. Like actually using them in your proofs could be pretty weird. And also there is the question of how do I derive good induction principles for that sort of stuff.
Yeah.
There's some very interesting questions going on that is highly non-trivial, I think. So how do you deal with inductive properties in Cedille2? Talking about this, since we're at this.
What do you mean? Do you just mean like an inductive type?
Well, my point being is that, okay, so let's go from the beginning. We don't have a built-in notion of inductive data types. So when you have inductive data types, one thing that you really want to do is induction, right? Which is basically, it's recursion, right? You want to recurse over your data because your data is recursive and you want to recurse over your data. Otherwise, you cannot do proper functions over them, right? In Cedille, we don't actually have a built-in notion of data types. So there must be a strategy in Cedille in order for you to derive these induction principles, right? So what did you learn from Cedille and how are you applying those things into Cedille2? And also, like, since there is this somewhat fundamental difference between the encoding of your data, right?
Right. Okay. So here's the secret sauce. Every construction in Cedille is actually just a quotient type. There you go. So every time we build an inductive data type, what do? First, we define an approximation, usually as a system F omega type. In our case, usually we start as a Church encoder. And then we define a predicate to define the canonical elements, which just happens to be the induction principle.
Yeah, that's a neat trick. I remember this. Yeah.
So
it comes almost for free, right?
Relative to the element you're canonizing, basically, not in general. Right. Then you intersect them, which in my mind cannot look like anything but quotienting at this point. You quotient them, and then that type is sufficient to prove the actual induction principle about.
But you still have to derive them.
You do have to derive them. So do you want to know like the steps, the actual steps to derive?
I don't need to give me the proper steps, but a high level idea would be nice.
Basically, because it's an induction, because it's a quotient, you prove that you first define the canonizer, which goes from the approximation to the full guy, the full type. You prove that the canonizer is extensionally the identity. So starting to sound familiar with the phi roll.
Yeah.
And then that's enough. So when you define induction, you just use the canonizer with equality to like shift the type view in the right places. And then you can just, because the approximation has enough of its recursive content, right? It's the same object. It's the same recursor. It has enough information that you just kind of use it. You just say, oh, I have my 0 case here, I'll plug that into the 0. I have my successor case here, I'll plug that into the successor, and then you're good to go.
Yeah. Cool stuff. You're going to say something then? You good? We're following still?
No. But I'm sure our listeners are.
Okay, I'm going to rant a little bit for a moment. Perfect. For some reason, a lot of times when I talk to people, even in computer science, they don't understand what a quotient type is. And it's like very frustrating to me.
So because I have a confession. I don't understand what a quotient type is.
You're not the only one. Yeah, you're not the only one. It's very frustrating to me because it's like integral to Cedille, and I also think it's integral to homotopy type theory. I'm pretty sure there's a paper out there somewhere that if you just add like the higher order quotient type and maybe like a few, like maybe the circle type or whatever, you get like all the higher inductive types. Right, so the quotient type is like a pretty powerful concept. And it's also used in math literally all the time. In fact, you've interacted with it in high school math. It's called the rational numbers. The rational numbers are a quotient type or a quotient set, if you want to be set theory. So this is my rant, is that you people really should know what a quotient set is. God darn it.
What's that?
Well, okay, yeah. Let's get the soundbite. What's the tutorial for the 1 minute define crash course of quotient types?
Define the quotient of the set of the rational number.
Yeah, so for the rationals, it's easy. First, you define the fractions as pairs of natural numbers.
Okay, we have your pair. What do I do
then
with it?
Then you define the canonizer, which produces the reduced form.
Okay,
right?
So I pretty much get the denominator, the common denominator, the least.
The least. Yeah, you do Euclidean's extended algorithm to get the reduced form.
Okay.
And then the set of elements that are canonical is the quotient set.
So it's canonical to respect to this. Oh, it's quotient to respect to this canonical form.
Yeah. So that's how you do it for the rational numbers. A more general construction is you say, okay, give me anything. Give me any old type A, write an equivalence relation over that type, and then the quotient is the set of canonical elements relative to that equivalence relation.
Right.
Or the type
Yeah.
of canonical.
Oh, that's so nice. That's so simple.
It really is, yeah. I think people do know it, they just forget. Or they don't,
No,
it's so simple they don't bother to piece it apart.
You know what's the issue is that this idea it comes from algebra. So like in algebra, this is pretty common, but it's something that we've been losing in computer science. We are not studying that much of math and algebra anymore. That's my feeling, at least, right? I did this introduction to algebra course, but we don't think in those terms. In many of those terms, it's kind of like being lost, which is it's sad, I would say.
I agree. You should learn some algebra.
Exactly. Yeah. Like we are all super hyped up. Let's talk about category theory, and we don't even know basic algebra, to be completely honest. Especially here in the US, we've been going. Computer science departments are going too much into engineering these days, especially with this humongous rise of AI. And kids we're not teaching, algebra or even logic is being kind of lost, in some sense. But, But, it's important. That's where all these ideas come from. That's where our field definitely was born from, right? It was in logic and then from math. So it was a good explanation.
Yeah, I agree. Mm-hmm. Learn your math, kids. Stay in school.
I agree. So quotient types and quotient sets is very interesting, because then it's a really good way to make partitions over your set, right? And talk about all these elements that in the end of the day you don't care about their differences. That's why you carry around this equivalence relation, right? They're equivalent with respect. I mean, everything is equivalent, just respect with some equivalence relation, of course. But you're partitioning your sets in all these different ways, and now when we bring this to type theory, dependent types, and all of that, then it's a nice way to talk about different objects that, in the end of the day, you don't care about their differences, right? Like you're collapsing the structure in different forms, which can be very powerful. Yeah, thanks for that. Well, with that, I think we covered pretty much everything that we had to cover. But is there anything else that you guys would like to bring to the table before we wrap it up?
You're going to Midwest Programming Language Summit, right?
I will be there. Yes.
Yeah. Well, for the viewers out there, go to your local stuff.
Right.
So why not?
Yeah.
Meet people, network. It'll be fun.
I sent this invitation, and we have a Discord now for the Type Theory for All podcast, and I sent an invitation inviting everyone to come to the Midwest PL Summit, which will be there. You'll be there, right, Andrew?
Yeah, I'll be giving a talk there.
Dan is a sucker, and he will not be there. But
that's okay.
We are also planning to do some gathering in Chicago, in the Chicago area, in the near future. So keep tuned for that. Right, Dan? We are, right?
Mm-hmm.
We are, right?
Yeah, thinking about
it. Okay, good. Well, so if we don't have anything else to talk about, that was a big pleasure to have you guys here. Thank you so much, Andrew, to come and share your knowledge with us. Thank you, Dan, for joining us as well.
Yeah. See you next time, I guess.
See you. Bye-bye. Well, that was it for today's episode. Thank you so much for listening until this point. If you liked what Andrew talked and you are a professor, he is currently looking for postdocs, so I'm leaving his email on the description of the show, and please contact him. He's really cool. Anyways, don't forget to join our Discord. Don't forget to donate in our Ko-Fi platform. Send us messages. We have an email, typetheoryforall@gmail.com. Go to our website. We also have a comment section over there, typetheoryforall.com. And I think that's it. I'll see you guys next episode. I think this is one of the most technical episodes I've done.
It got really
Right?
technical, like right away. I didn't realize you did any work on Cedille. So this was like this is in your master's degree? Wait, do you do a master's degree? How did that work?
It's something that I was working before doing the work on. So how it worked was that I was doing some parallel programming, actually. Reasoning about parallel programming my first semester, I think. And then I went to Galois. Yeah, the first year was that. And then I went to Galois. And when I came back, I started talking with Ben, and Ben sent me to Iowa to talk with those guys, with Aaron. And we started contributing for another year, more or less. And then, because I was thinking so much about functional, about pattern matching, because it's a big deal in Cedille, right? Because then pattern matching is the eliminator of data types. So Cedille, your data types, like it's kind of central to the discussion. And so dealing with pattern matching is also central to the discussion. And I was trying to do some translation of Cedille to Coq, right? Cockadille, inside Coq, which was kind of fun. And then I found this project on GitHub that was doing similar thing, but all camel to Coq. And I contacted them asking how they dealt with something that I was trying to do, which is pattern matching, like how to translate pattern matching properly. And they're like, we have no fucking clue. And I'm like, okay, let's work together. And then I went there. And then that's how I ended up working with this other stuff.